Hi mates, so the previous video we've implemented Minecraft redstones and torches digital logic in pure JavaScript, but I've significantly improved the application that we built in that video since then. So let me first quickly demonstrate you the updates, and then we'll get to the very topic of this tutorial, which is implementing logic gates within this particular emulator. So if you're interested, without further ado, let's get started. Okay, so first of all, from now on we can set up the manual board size, like for instance like this, and reset. And bear in mind that if you click the reset button, if you had any work being saved, that just gets vanished. So we can also change the cell size like this, and whatever combination is okay. But let's drop back to the original version, which is this. Okay, so I've added this start stop button. So this is just a browser application, just to give you an idea, so just maximize this. Now whatever tool is currently available is highlighted nicely, and the start stop button allows you to toggle between like draft mode, architectural mode, and the simulation mode. Although you can make updates within the simulation mode as well, but it just might get a little bit laggy, so it's better to like draft and then start the simulation. And also we can now download our work and upload something from the file like this. So here I have just a string. So if I just get this string and I just put this here and say set, then I have like something being uploaded. So this is the generator, and this is just inverter. All right. Also, we can change the simulation speed, so it might go like 100 milliseconds per tick, let's say, and up to 1 second, so just the slowest possible way. But let's drop back to this one. Okay, so now if I just stop the simulation, and again, so I just want, let's say I just added some more, I don't know, just added some wires here. I can just click this get, and I then just copy and paste it to the text file like this, and I have like this string is not exactly the same as this one, so just to give you an idea. So now for instance I want to copy this update, and if I just update the screen, everything gets vanished, so I just put it back here and set, and this update is now being available. So hopefully that makes sense in regards on how to use the particular application. Now, without further ado, let's dive into building logic gates. So we will start with the most simple elements and then get more and more complicated. So let's consider the switch, and then some wires and the light by the end. I'm not quite sure in regards to the name of this gate, so someone call it yes gate, someone call it identity gate. So the idea is very simple. So whatever you have on the input, exactly the same thing goes to the output. So operate, and I turn on. So input is 1, output is 1. Input is 0, output is 0. So switches can be treated as inputs, and lights can be treated as outputs. But also wires, which are green, this not rectangles, this tiny squares, they literally work in exactly the same as the lights do. So hopefully that makes sense. So this is the easiest possible one. And the next element, the next basic element, is the inverter. So I just put the inverter in here and put some wires like this. So that is something that we've already seen. so nothing new so far. And I just start the simulation. So this one works the opposite. I forgot to click on this operate button. So in the first case, input equals to output, right? But here, if the input is equal to 1, so it's powered up, then the output is equal to 0, so it's turned off. So hopefully this makes sense. So this inverter, literally what it does, it inverts the signal. And already, based only on these two elements, you can build anything up to the entire computer, for instance, like the CPU or something. Probably this won't be enough space here to place all the elements, assuming they are drafted this like way, but in theory this should be possible. So now let's get to some more complicated gates. So just here, I believe. So let's try OR, NOR, and NAND for now. So there are two ways of how you can implement the OR, and I will now try to explain the difference between those two. So we take the switch like this. So the simplest possible way you could have ever imagined is the following. So like this is the pure logical implementation. So I just need to stop because it just gets a little bit laggy, also because of my video recording software. Okay. So if I start this and operate, so you probably aware of what is known as the truth table. So the truth table, it mentions the inputs and the desired output for the certain gate. So the truth table for the OR is the following. So 0 or 0 results in 0, 1 or 0 results in 1, 0 or 1 results in 1, and 1 or 1 results in also 1. But if we, for instance, we can use it if it's not interacting with some other complicated parts in our schema. But for instance, if you want to try to implement the XOR gate, this implementation is not relevant. So to make it, because it's just transparent and the current would be flowing through it, so it's not what you're supposed to be not what you're supposed to have as an output, as a desired output. So to make the same OR gate, but to make sure it can be used as an element, like for instance in here. So here we have the NAND, and OR. So if you want to implement schemas like this, so there is another like proper way of implementing the OR gate, just at the very least to make sure this is supposed to be working under this emulator in particular. So let's give it a try. So just stop the simulation here, and this is going to be quite similar. So I just start like this. So we can just put two inverters in between, like this. And because of these inverters, you can connect the inputs to like embed them into your schema, and not being afraid that it would be transparent to the current. Okay, so light and operate. So same thing. So 1 or 0, 1, 0 or 0 is going to be 0. And we can make it a bit faster. Okay, 0 or 0 is going to be 1. 0 or 1, sorry, and 1 or 1 is going to be equal to 1. So hopefully this makes sense. Now to turn this one into NOR, I do exactly the same way, but I just put one more inverter in here to swap, to invert the output signal. So this is how it's supposed to be done. So just put the switch, okay, just starts being a little bit laggy. So like this, and then I put this inverters. So again, if you don't need to use this somewhere where it's not required, you can just use this version, but sometimes you need this one. and like this. So the idea is that NOR is OR, but after the result has been achieved, it just inverts the result. That's it. So for instance, if we start the simulation, so 0 or 0 is going to be 0, but if you invert this, it would be 1, just like it's here. The same, like if we do, okay, if we do like 1 or 0, it would be 1, but inverted it would be 0. Same for this one. So this is like 0 or 1, I mean 0 nor 1 to be exact. So it just gets inverted again, and here is also going to be 0. So it just works like OR, but with the inverted signal. Now let's make AND. So to make the AND, I take the switch and like this. So we also need a couple of inverters like this, and then like this inverter, and then wire and the light. So the truth table for AND gate is the following. So 0 and 0 results in 0. What we have 1 and 0 results in 0. Okay, doing this again and again. 1 and 0 results in 0, and 0 and 1 results in 0, but 1 and 1 results in 1. So this is how it works. Now NAND is exactly the same as the AND, but we need to invert signal at the very end. So instead of putting one more inverter here, we can just get rid of this one. So in that case, it's even simpler. So we just take a couple of switches here. So we just take it like this, and what else? Inverter, and that's it. So we just do like this, and the light, and operate and start. So 0 and 0 is 0, but it's inverted, hence 1. So this is NAND. Same for 1 and 0 is 0, but inverted is 1. Same for 0 and 1, but inverted, but it is 0 and 1 is 0, but inverted is 1. And 1 and 1 is 1, but inverted is 0. So these are the basic gates like OR, NOR, AND, and NAND. And now let's get to more complicated ones like XOR and XNOR. So here, here is the schema, like how can we build the XOR using the NAND, and OR. I just need to duplicate this one, which is the AND. So let's make a couple of switches like this, and take the inverters, and also one here. Okay, and so when you're working with inverters, you need to make sure that the input goes from the bottom while the output goes from top. So otherwise it's not supposed to be working. Okay, and put the lights on top. So this is the AND. Okay, now we have NAND on the left. So let's just create NAND in here. So the output of the NAND is the left input of AND, just to give you an idea. So the output goes to the input. So here, so this is the output for of the NAND. So let's make it and put inverters in here. So yeah, I don't need switches for now. I can just consider the wires here. But yeah, just for clarity, for now I can still use the switches. I will then get rid of those because it's not going to be working with the switches, so I just need to get rid of those. And here the OR, all right, so output of the OR gets to the another input, to the second input of this AND. So I will now use this OR. So just to give you an idea, if I use this OR, so let's start simple, just to give you an idea why this is not possible. So if I just use this OR, then the problem here, switch, comes a bit later. So we just now need to connect these two, so the left one of the OR with the right one of the NOR, of the NAND, I'm sorry. So literally, so these should be connected, okay, and then this gets connected to this one, so this gets connected to this one. And input would be in here, the first one. The second input is here. So, and we don't need the rest of the inputs. But you see what's the problem in here? The problem is that when we have one in here, it just goes to OR, but it also would power up this one, which is unacceptable. So just to give you an idea, so we just start the simulation in here. So just operate, and so you see, like, it powers the OR. So here we have the OR, but it just transparent and the current flows to where it should be, where it shouldn't flow, where it's not supposed to be flowing. So in order to avoid this disastrous scenario, we're supposed to be using this version of OR, with just two inverters. So we can do this like so. So we can put a couple of inverters like this. And in this case, so you see, if we do the same now, we just power this up. Okay, powering this up. So now, although this one is powered, you see, but this one is no longer powered. So this is how we make use of the inverters that the OR gate is built of. Okay, now let's check the truth table. So 0 XOR 0 is going to be 0. So exactly what we have. Now 1 XOR 0 is going to be 1. So if I put, and same for 0 XOR 1, also going to be 1. So if I put either of these two switches, the light should turn on. So just, and it turns on, which is correct. And if I turn on the second one, this one, it should also turn on, which it does. Okay, and 1 XOR 1 is supposed to be 0. So once I turn this one, the light should go down, right? This is how it works. And now to invert this, again, we can either put another inverter or we can just get rid of this one. So now let's just stop the simulation, taking the wire, put it in here, operate, start the simulation. So now it would be XOR, but then with an inverted signal. So 0 XOR 0 is 0, but we invert, so we get 1. Okay, now 1 XOR 0 is going to be 1, but we invert and we get 0. So once I put this, it should just go off. And same if I turn this one. Okay. Now 1 XOR 1 is supposed to be 0, but since it's inverted, it would be 1. So once I activate both of them, it just lights up. And using only this simple logic gates, we can start building way more complicated systems like latches, flip-flops, like 1-bit or 8-bit memory registers. And with the combination of the clock that has been already like demonstrated in the previous video, but I can very quickly give you an idea how the clock is supposed to be working. So for instance, like if I just do like just 3 inverters like this, and if I connect those, and for instance I just drop back to just make inverter in here, so this is XOR, and for instance I can just want to put the clock cycle, the clock signal to one of the inputs. So for instance for this one, okay, and like this. And now this should be, this one would be either 1 or 0. So this would be 0, 0, and this is going to be 0, or 1 and 0 is going to be 1. So this clock should now make this light blink. Let's give it a try. Okay, seems like it does. See, like it really does. Okay. Nice, isn't it? So yeah guys, this is from my side. See you later and cheers.